Hi everybody, welcome back to Chem 140. Got my seltzer here. Let me wind the music down here. Alright, what do we got going on today? So, we're going to start by talking about the lab for a little bit. The lab is very straightforward this week. It's like the lab from the first week. That'll be due next week. But more pressing on the upcoming agenda is that Quiz 4 is due tomorrow. Quiz 4 is what, units 7 and 8? So that will be due Wednesday. Make sure you get that in by the deadline. That is a soft deadline, so if you need an extra day, that's fine. What's the next quiz? The next quiz is 9 and 10. So once we finish Unit 10, quiz number 5 will pop up. And then after that, the quizzes are... yeah, they're going to be more or less evenly spaced, because those units are a little longer. Okay. Where am I going? I am going to this screen. We're not going to deal with this just yet, because I want to talk very briefly about the lab. Let me get the lab on the screen here. There we go, that's the one I want. Boop. That's not at all helpful, though. Hold on. And we don't need my browser bar. Ah, there we go, okay. So we'll just do that. I'm going to scroll down to lab number 3. So lab number 3 is another sort of observations lab that deals with ionic compounds, which ironically is what we're doing right now. So, oops, let me get the worksheet going here. Close this. We'll get that on the screen. So, what lab number 3 is a video of another faculty member, Samita. Samita's our department chair. She also teaches a lot of 140. So, basically, you had two options when taking 140. You get me or her. Sometimes other people do it, but Samita and I do, for the most part, all the 140. So we work together. She made a video, and I edited the video. And so you'll watch a video of her doing the flame test. The flame test is common in terms of things that you see, because it's basically, what do elements look like when you burn them? And you see that all the time in July, which is coming up, right? So fireworks are lots and lots of pretty colors. What goes into fireworks? You're going to learn that in this lab. You're not going to learn why this happens until 161, when we talk about atomic emission and why specific colors and wavelengths come out of specific atoms, particularly hydrogen. We're going to look at that in 161, why hydrogen is purple when you, not when you ignite it, but when you electrify it. But many elements have very specific transitions that emit a particular photon of light that gives you a particular color, which is why we use them. And we can use this as a way to identify things. This is just a discussion of ionic versus molecular compounds, which we're going to talk about today. But this is relevant for part 2 of the lab, which talks about conductivity. The lab will be Samita putting various solutions and then a conductivity probe, and you're going to just basically observe a graph, or it's more a number, that will increase if the solution conducts electricity, which means ions are present, and it will print 0 if the solution does not conduct electricity, which is if molecules are present. So like all labs, you're going to have a pre-lab section with a bunch of questions that you enter in. Then we have the experimental tab, which is literally just going to be observations. You're going to watch the video and type in what you see. Be specific with your color descriptions right here, because what you're going to have to do is match them up to these unknowns down here. The unknowns, there are 3 unknowns, but they are numbered 1, 3, and 5. There is no unknown 2 or unknown 4. We just didn't use them that day. These 3 unknowns are one of these solutions. Okay, so try and identify them the best you can. For one of them, it is tricky, but for this lab, I'm only going to accept the correct answer. Depending on what frame you stop the video on, you might think that it is a different answer, and I try to stop the video on a really specific frame that makes it obvious what it is, okay? So be careful. If you have issues perceiving color, talk to people in the Discords, get their opinion on it, because there is one definite answer for all of these. Down here, you're going to just record the number that you observe for the conductivity test. If the number fluctuates, just enter any number you see. We're just going for approximations here. And then finally, analysis questions, which are talk about the things that were done in the experiment, tell me what the unknowns were, tell me why you think that. So be specific. I think unknown number 5 is this because this is what I saw. I also saw this in the blank. Don't just say, I think it was unknown number 5 is that because it's blue. You need to cite actual observations. So make sure you're answering these questions correctly. Down here, issues that get a bunch of people, make sure you are answering the question. So when I ask you which solutions are conductive, list the specific solutions. Make sure you are putting the solutions in there and not just saying, oh, it's the ones with X. I want you to be more specific, so be specific. Number 14 is a question that gets a lot of people, and it confuses them. My advice for this is that I want you to think about what kind of compound potassium hydroxide is. You're not actually testing it in the experiment, but think about what conductive solutions care about. What is it in the solution that conducts electricity? Then think about what KOH can do. And I'll give you a hint, KOH is soluble in water, so it does split into ions. It splits into K and then OH, which we're going to talk about today. And then use that information to write your answer, okay? Most of the rest of the questions people do really well. The other thing I would mention is that for 13, when I say a roughly linear relationship, I mean pretty rough. Like, does it look fairly linear? And if it looks random, say no. And if it looks sort of linear, say yes. That's really what I'm looking for. Okay. That's really it. The last thing that I would say about this lab is that the video that you need is in the documentation. There isn't a link elsewhere to it because it's just this one unlisted video. So yeah, you do need to copy and paste this link into your browser. You should get a video with Samhita in it. So let me cue that up for you so that you know what it looks like. And so if you have the right video, it should look like this. This is what the video should start by looking at. There's Samhita right there. I put her portrait on the screen at some point. Where is it? Just so you can know. There's Samhita. So just in case you were wondering what Samhita looks like, there she is. Because she is the sort of headless entity that never really is seen in the video. It's kind of weird. So I was like, okay, we'll put her picture there. But if you see Samhita on campus, go tell her that you love her video, whenever we open back up. All right. That's all I have to say about the lab. The lab is very straightforward, and it deals with what we're talking about literally right now. So let's keep talking about it. The other day being Monday, sorry, I always preface the other day for my classes because I teach sections on different days. We're Monday and Tuesday, so on Monday, we talked about how ionic bonds form. So first there was the general nature of ionic bonding, which was positive and negative charges attract to each other. Then we ended with the discussion of how do we get to the point where we have charges. And we concluded that in order for atoms to follow the octet rule, they need to shuffle electrons around so that the result is octets. So this has an octet. Remember that 0 counts as an octet. And this has an octet. The octet that forms is the end ion that the atom will adopt as well as its charge. So because we removed one electron from sodium, it adopts a positive charge. Because we added an electron to chlorine, the chloride ion gains the negative charge. If we move more electrons, we will get more charges, as you're going to see in some of the examples that we do in a second. So that's the order of operations here. First, you have to make ions. In order to make ions, we transfer electrons. So electrons must be transferred so that both atoms have octets. That's how we make ions. Then once we have the ions are then attracted to each other because positive and negative attract. All right. So now our goal is to figure out specifically what formulas are created for any pair of elements that I put together, any metal and any non-metal. And that's actually very straightforward. First of all, we are going to operate on this premise. Ionic bonds form between metals and nonmetals because we need something that gives away electrons. So that's this. And we need something that accepts electrons. Later in the lecture, we're going to talk about covalent compounds, which are just nonmetals. We're not going to do metallic bonding, which is just metals in this class, but it does exist. So in case you're curious, you can go look that up on Wikipedia or something like that. Or if you take a material science class, you'll talk about alloys and the formation of metallic bonds and stuff in those courses. All right. How do you predict the formula for an ionic compound? With sodium chloride, it was really easy because in order to make everything have an octet, all I had to do is move this over, and this was satisfied, and this was satisfied, so we're done here. But in some cases, you might need to move more than one electron. For example, here's magnesium and chlorine. And so we'll put the same 7 electrons around chlorine and the same 2 electrons that magnesium would have. I could do this and move this over so that this has an octet and that this one is no longer here. But then I still have to do this. I have to do something with this electron. Where does it go? I can't give it to this chlorine. It already has an octet. So what I need to do is I need to find a second chlorine to give it to. So here would be my second chlorine. I can give this electron to that so that this has an octet, and now this does too. You can always get another atom of whatever element you need because there are quintillions of atoms in your sample, right? You're always going to find one more. So when you're making formulas, assume you have abundant atoms available and shuffle electrons around until everything has an octet. Now that everything has an octet, we just index how many there were. There was 1 magnesium, there were 2 chlorine. There's our formula. If you move multiple electrons to the same atom, it doesn't matter. For example, here's what sulfur would look like. Sulfur needs 2 and calcium has 2, so we'll just pass them both over. This is good, there's our formula. And you're all set. Sometimes this will get convoluted. You will have to get multiple of many types of atoms in order for the formula to work out. We're going to look at a bunch of examples in the Now You Try in just a second here. Whenever you write the formula for a metal, or a non-metal, for an ionic compound, metal goes first, non-metal goes second. Put the positive part first. So instead of writing CAS, don't accidentally write SCA. Canvas will mark it wrong. Always put the positive part first. Put the metal first. Now, a consequence of us doing all of this stuff, and we'll go back to the magnesium and the chlorine example here. So let me just put my dots in real quick. There we go. I'm going to pass 1 electron over to this chlorine so it has an octet. I'm going to pass 1 electron over here to this chlorine so it has an octet. This magnesium now has an octet. If I write the ions that we have formed, this is the charge that I have formed on magnesium because I got rid of 1, 2 electrons, right? Each chlorine accepted 1 electron, so it will have a negative charge. Now, if you sum together all of the charges, you'll notice that the total ends up being 0. And this is just a consequence of the octet rule. The total charge of an ionic compound must be 0. When we get to ionic compounds that don't follow the octet rule, they still follow this charge rule. For instance, if I start giving you transition metals, which, again, remember, they don't follow the octet rule because transition metals are weird, they will still sum to a total charge of 0. In other words, all your positives have to equal all your negatives. So let's look at an example of that, even though we haven't really quite gotten to that. So let's suppose that I give you this compound with a +3 charge, and I say we're going to bond it to oxygen, which has this charge. How many of each do I need? Well, if I combine these together, that's no good. I don't have a net 0 charge, right? So the ionic compound I form would not be oxygen. I would instead need multiple of each. Well, as is shown, I have too many positives, so I'm going to add another negative here. Now I have too many negatives, so I got to add another positive. That's still too much positive, so I'll add another negative. And at some point, when you do this enough, you will eventually get 0. And so that would be the ionic compound between iron with a +3 charge and oxygen with a -2 charge. Now, always remember that you know what charge some of these will form. I misspelled it. So when we start working with transition metals, and you're like, oh shit, how am I supposed to figure out what the charge is on the ionic or the metal part? You always know the nonmetal because all of the nonmetals follow the octet rule. They're all in groups 1 through 8A or groups 1, 2, and 13 through 18. Over here, these charges will be given to you, or you can deduce them. But in some capacity, these can be solved for. All right. So let's get you some problems so that you can try these. I'm going to combine these two things together. What formula will you make? Go ahead and just drop the ions on a piece of paper. So just write K plus and S2 minus, and then add extra ones to whichever side you need more charge to. And keep doing that until the total charge is 0. What you end up with when you do that is your formula. Again, your formula is just how many of the ions you put on your paper. Okay? Type that formula into the chat once you got it. And we'll go over the answer in about a minute. All right, and you have the right answer. Very good. So let's show how you got that. So I'm going to just put the ions down. You can see too much negative doesn't balance out to 0, right? So let's put another one. And I'll just show the entire math here. So 2 times 1 plus is 2 plus, and 2 negative. When we combine those together, we get 0. So this must be my formula, K2S. All right, you get the idea. Let's do that with transition metals. So, oh, we already did this example. Damn it. Okay. Well, you can rewind the video to see that. So, I'm going to hand you some examples. Here you go. And so what I want you to do is use the strategy of put the elements together in their ionic form and then make the formula. Now, you'll notice that I omitted all the charges because I'm a jerk and I want you to do all the work. So what you're going to have to do is you're going to have to make these into their ions. So for example, for this first one right here, for potassium, here's what potassium looks like by itself. If I want to make it into an ion, I got to get rid of this electron here to make it have its octet. Then do the same thing for bromine, and then see what the formula is. As you do these, type the formulas into the chat, and we'll go over the answers in about 5 or so minutes. Let's do 2 or so more minutes and we'll go over the answers. All right. Let's go over the answers here. I'm going to hit clear on the screen real quick. Actually, you know what? Let's go over here. And we'll zoom this in. All right. So, let me just draw here where I can't draw in. So, don't use this. Okay. All right. So, for KBr, for potassium, I need to get rid of this electron. So, we'll just send it off. And that becomes K+. For bromine, I need to give it an electron from somewhere. And that would become, oops, Br minus. And I can see that these two together will balance out, so my formula will be KBr. All right, so the next one, I think we already did calcium and oxygen, but same process. We'll get rid of these two. That's the ion that forms. And then for oxygen, oxygen starts with 6. I'll give it an electron. I'll give it another electron. That's what my oxygen looks like now. And you can see that those two charges balance out because they're equal. So my formula must be that. And then for magnesium, I need to get rid of its electrons. So I have that. I'm going gonna run out of space here. Each chlorine starts with 7. I can give it an electron. And then I will have chloride, which looks like that. These charges don't balance out, though. So if I sum these together, I get +1 still. So I need another chloride to balance it out. Now it's 0. And so my formula would be MgCl2. And then I'm going to try and cram it in here. Sodium has 1 electron. We're going to get rid of that. There we go. Here's my nitrogen. Nitrogen has 5 valence electrons. I got to give it 3 electrons to get my octet around it. And you can see that those charges don't balance out at all, so I need more sodiums. That still doesn't balance out. That's good. There's the formula. For the last one, I do have to hit clear on this, unfortunately. So scroll all the way back up to the top because we're going to use a lot of space for it. Hold on. For aluminum, here's my aluminum. I'm going to get rid of its 3 electrons. Goodbye. That's the charge I form. Oxygen has 6 valence electrons. I'm going to give it 2 more. My charges don't balance out. I have too many positives, so I'm going to add in another oxygen. Now I still have too many charges, but I have too many negative this time. And so you just sort of do this back and forth game until you have an even number of each one. So now I have 6 positive and 6 negative. My total charge is 0. And then my formula would be Al2O3. And there you go. That's how you make ionic charges from neutral elements and then put those together to make ionic compounds. Any questions, let me know in the chat. All right, for the next exercise, what I want you to do is I'm going to give you pairs of ions this time, but some of them are transition metals. So what I want you to do is put these together to make their ionic compounds. So I've already done the octet part for you for the elements that follow the octet rule. Down at the bottom, titanium and vanadium don't follow the octet rule. So you'll need to predict the compound by just using the ionic charges that I have shown for you. Okay? So same as last time, write the formula units for each ionic compound and put your answer in the chat when you're done. I'll give you not as long this time, 3 minutes to do it. All right, one more minute. We'll go over the answers. I've already gone way over my target time. That's okay. All right, so same premise as before. I'm on the wrong screen for this. There we go. We're going to write out ions until we have everything balanced out. So for barium and iodine, those obviously don't balance out. I have a remaining charge. So I'm going to add an extra negative so it balances out. And there's your formula. Here, my charge doesn't balance out. I have too much positive, so I'll put another S2 minus here. Doesn't help me, though. Still doesn't help me. There. So some of these take a while. You just got to put extra ones down. We already did sodium and azide, or not azide, but nitride here. So I'm going to skip the counting part and just write out the answer here. For the titanium and oxygen part, you'll notice that, oh, I just need a second one of these to get 4. And there you go. And then the last one down here with vanadium and phosphide. This is sort of a mess because you're just going back and forth. So this is -6, that's +5, so I need more of this. Now I have +10 and -6. This is -9, that's still not enough. -12. So now I have +15 and -12. One more gives me -15. So this is +15 on the top. This is -15 on the bottom. Those balance out. I can now make the formula. So as the charges get bigger and they don't divide into each other, you get more and more obnoxious compounds. So, all right, any questions, let me know. We have ionic compounded. All right, let me check something real quick. Yeah, we'll do this last bit, and then we'll take our break. All right. So now the next thing that we got to do is we got to work backwards. Putting ions together to make the formula is great, but there's also a use for knowing what ions are in a formula. So if I look at my compound, I need to remember that for groups 1 through 8A, which again, remember are groups 1, 2, and 13 through 18, we're going to deal with ions that have a known charge. So if you ever see something that's in groups 1, 2, or 13 through 18, you automatically know what all the charges are because they all follow the octet rule. So for instance, if I asked you this weird compound here with cesium and arsenic, that sounds awful. Well, cesium is in group 1. So it's going to look like this, and you can get rid of its electron to make it look like this. Likewise, arsenic is in group 15, so it's going to look like this. 1, 2, 3, 4, 5 electrons. We'll give it 3 more. So that it becomes arsenic 3 minus. I forgot my brackets over here, but that's okay. So those would be the ions that form from this compound. Would be cesium with a plus and arsenic with a 3 minus. I don't really care about how many there are. I just want to know the charges on the ions here. But you would need 3 of the cesiums to make cesium arsenide here. All right. If you have a transition metal, you don't get to know the transition metal right off the bat, though. What you need to do is solve for the other ions that follow the octet rule. And this kind of will answer your question of what's the largest compound you can think of, because you can put any two numbers together, and if you get numbers that don't divide into each other, like 8 and 3, you're going to have a ridiculously complex formula. So remember, again, at the end, the total charge has to be 0. So let's look at this right here. So tin is in group 14, but it actually doesn't follow the octet rule, because you would think that it would be -4 because it's in group 14, but it's, remember, group 4 is weird. But oxygen is in group 16, and so it follows a regular pattern, and you should know by now that you make this out of it. Well, if I have 2 of them, I have a total charge of -4. That means that whatever tin is has to exactly counteract the -4. Therefore, it must be +4. So you can deduce what the charge is on an ionic compound once the formula is made by breaking apart all of the ions, calculating the negative charge, and then solving for the positive one. If you have multiple positive ions, you have to split that charge amongst them. So if I had something like, say, this, which we've already solved already, you know that this is what your O's are, your oxides. So that totals up to -6. My 2 irons would have to sum to +6, which means that each one must be this. All right, so there is going to be some algebra, in a way, involved here. All right, so now that you understand that, here's a bunch of compounds. And what I want you to do, is break them into ions. Start with the ones that you know. In some of these cases, you will know all of them, and you could just write them out real quick. So, like, for instance, aluminum bromide, that's easy. You know what aluminum forms because it's in group 13. You know what bromide forms because it's in group 17. But down for the last 4, you don't know what osmium does. You don't know what rhenium does. You don't know what gold does or scandium. So you have to use the other things to figure it out. Okay? Type your answers in the chat once you've got them. To the best of your ability. I realize that it's hard to type superscripts and subscripts. And we'll go over the answers in a little bit, and then we'll take a break. All right, one more minute. We'll go over the answers, and because we're due for a break here. All right, so let's go back to this screen. And we'll get rid of all these. Where'd my pen go? There it is. Okay, so the first one, you already know what ions form for aluminum and bromine because they follow the octet rule, so that's easy. And the same is true for calcium and chlorine. So these all follow the octet rule. So easy enough. But the last four are a little bit more challenging. So here we got osmium. And I've got 4 oxygens. And each oxygen, when in an ion, makes O2 minus. So something's got to go in that circle that balances out 8 minus. And that is 8 plus. And you might think, what the heck? Can a transition metal lose all of its electrons? And it turns out, yeah, again, transition metals are weird. So you could totally have plus 8. For rhenium, again, same issue. I have something I got to put here, and I've got a bunch of chlorines. Okay, what must go in there? Well, it's got to be this. How about for gold? Now, in gold's case, there's 2 golds, and you have 1 oxygen. Oops, my pen didn't change the thing there. I don't know what goes in these blanks, but I do know that gold always forms 2 minus. So, what would I split the positive among to total 2 minus? So, remember, these got to add up to 2 to cancel this out. And that would just be, they're each plus 1. And then finally, for scandium, I got 3 of them, and I've got 2 nitrogens. Each of these is 3 minus because octet rule. But I got to fill in these blanks. Well, the total is -6. This has to equal 6 plus. 6 plus divided among 3 would be 2 plus. There you have it. So that's how you figure out what the charges are on your ions in any ionic compound. All right, when we come back from the break, we're going to throw polyatomic ions in the mix. So we'll see you for that. So I'll hit the button, and let's get the music going. All right, we're back. All right, let me get rid of this because I don't need that anymore. And let's continue. So, the last thing that we need to do when talking about ionic compounds is, what do we do with polyatomic ions? How do these fit into the equation? Polyatomic ions are already ions, and so I showed you the list of polyatomic ions way back at Unit 6. So you can refer to those slides. Hopefully you have them handy because we're going to be referencing them here. And all you have to do is just keep the ion as it is and use whatever charge is presented with it. So, for example, if I take calcium and phosphate here, I'm going to just operate under the same premise that I was with other ions. So I have a -3 and a +2. I need more of this. I guess we'll just keep the running tally here. So I had +2 and -3. So now I have +4. That's still not enough. Negative. So now I have -6. That's still no good. So if I do this, there we go. It balances out to 0. So what would my formula be? Well, I have 3 calcium, and then I have 2 phosphate. When I write my phosphate, I have to do it like this. And the reason that I have to do it that way is because I need the parentheses to indicate I have 2 phosphates, and not say 2 phosphorus and 8 oxygen, because I want to keep them as phosphate. There we go. So that's the formula that we'd get for that. So more or less, it's just the same thing that we've been doing, but now you have to find the polyatomic ions in there. And again, of course, make sure you have the parentheses, because obviously if you don't, then those numbers look very, very different without, and that would be wrong. So when typing your answer into Canvas, put the parentheses around the polyatomic ion. Don't put any spaces there. Just type in Ca3 parentheses PO4 parentheses 2. All right, so I've got some combinations here. The top stuff should be pretty easy because it's the same principle before, but the bottom one is going to require you to know your polyatomic ions. So if you don't have them memorized, which, again, online class, probably haven't, that's fine. Look up the polyatomic ions, find what their charge is, and use that to figure out the transition metal it's stuck to. Or you can work with the metals that do follow the octet rule to figure out the charge and the other things. Okay, so make the ionic compounds for the first set of questions up at the top. Split those into ions for the bottom set. We'll go over the answers in about 2 or 3 minutes. Well, 4 minutes or so. All right, one more minute. We'll go over the answers here. All right, let's go over the answers for these problems. I'm going to just write directly on here because all we're doing is putting things together. By now that you should probably have figured out that you need 2 of these to get the correct charge, so that you balance out the charges. Same thing for this one. We're going to need 2 of this one to get Na2CrO4. Notice that if you don't have multiple of the polyatomic ion, you don't need parentheses. So don't do this. Oops, I forgot my 2 there. Don't do this and then not put a number after it if you don't need it, because Canvas will mark it wrong. So don't unless necessary. Okay, so if there's only one of them, it's not necessary. So this is the right answer. This one's not. I need 2 of these ammoniums. So that has to go in parentheses, but the SO4 does not. And then I need 3 of the hydroxide here for the aluminum. So I'd get Al, parentheses, OH, 3. For these down here, this is just a matter of looking up the polyatomic ion or using the elements that follow the octet rule to solve for it. So if strontium is 2+, because it's in group 2, carbonate must be 2-. Over here, you need to figure out what cyanide is. Well, I've already shown it to you up here, right? So you know that cyanide is minus. There's 3 of them, so iron needs to be +3. Down here, we know what potassium is because it follows the octet rule, and there's 2 of them. So sulfite here must be -2 to balance out that charge. And then we have this crazy nonsense right here. So phosphate is 3-. What must vanadium be? Well, you can do the same sort of strategy we did before when we had vanadium and phosphide, P3- in there, to get this as your answer. All right, so making ionic compounds and then tearing them apart follows the exact same rules, whether you are working with elements that you are turning into ions or polyatomic ions and manipulating those. Any questions, let me know. All right. The last thing that we're going to do in this chapter is just a little segue on how to differentiate ionic versus covalent. And you've probably figured it out by what I have hinted at. Covalent compounds don't have metals in them. Ionic compounds do. That's pretty much the main difference. But the nuances between the compounds that form are also important. So we already know these two because we've mentioned it. And we'll get to this little asterisk guy on the next slide here. Remember that ionic compounds require us to transfer electrons from one atom to another in order to facilitate the ionic formation. And the term that we use to describe individual units of, say, NaCl or whatever is called the formula unit. Now, for covalent compounds, they follow different sorts of rules, as we're going to see in Unit 10. And that is that covalent compounds do not transfer electrons, they just share them. And so we'll describe that in more detail in Unit 10. And the end result that we get is a molecule that is independent. Since there are no charges, they don't attract other molecules to them. And so they operate on their own. Now, what's this little important note that I have here? It's that if you have ammonium in your compound, it's very easy to accidentally overlook this and think, oh, there's no metals in this, so it must be covalent. But ammonium is a polyatomic ion, which means it forms ionic compounds. And so down below at the bottom, I have a bunch of ionic compounds that do not have any metals in them because they contain ammonium. Okay? So be careful. If you see ammonium in your compound, it's still ionic, even though no metals are present. Treat ammonium as if it were a metal because it behaves like that. Otherwise, the easy clue when looking at a formula is there a metal? It's ionic. Are there no metals? It's covalent unless ammonium is present, in which case it's still ionic. So here you go. Here are a bunch of different compounds. I want you to tell me ionic and follows all the rules we've talked about in Unit 9, or covalent, and we're going to have to learn something new about it in Unit 10. So label ionic or covalent. That's all you have to do here. Be careful on some of these, because I am trying to trick you. One more minute, we'll go over the answers. All right, let's go through these. So I'm going to highlight all the metals here. So we've got potassium and silver and iron and platinum. So these must be ionic. All right, and now we just have to look at the rest of them. So we have to look for ammonium. Remember, ammonium is this. And you'll notice that in this one right here, we don't have that. This is something different, and it has a very similar name. Ammonia. Notice the difference. Ammonia versus ammonium. So this is actually covalent, and this one's ionic. These other two, these are both covalent, because they do not have metals in them. Oh, I didn't even see what you had written there. But yeah, that one is ammonia. Ammonia is NH3. Ammonium is NH4. So be careful. And when you're looking at literature that has, when I say literature, I mean like scientific papers and stuff, not like a book that you'd read. When you look at scientific literature that has ammonia versus ammonium, they will actually just sometimes type out the word, and it's expected that you know the difference. So just be mindful of that. I think that's it for this chapter. Yeah, hooray. All right, what time is it? Let's see here. 6:40. I don't have enough time to start the next unit because it's really short, and I don't want to stop midway in there. So we'll just go like this, and where it says announcements. Oops, I guess we didn't do Unit 9. That's okay. But what I do want to add to this is that you do have a lab that's due next week. So we've talked about the lab. So lab worksheet number 3 is due. And I never remember. I have to look at the syllabus for this. So hold on. Let me find that real quick. Syllabus. Due week 7 on Tuesday. So that would be the 19th. No, that's Wednesday, the 18th. So lab worksheet number 3 is due Tuesday, 18 May. All right, there you go. So make sure that you put some time into working on that this weekend. And make sure that you get quiz number 4 in by tomorrow night. That is a soft deadline, so it'll close on Thursday. And we're going to come back next week on Monday. We'll finish Unit 10, and we'll probably start Unit 11 because Unit 10 is only like 20 slides long. And a quiz will go up then because the next quiz is Units 9 and 10. Yeah, that's it. Have a wonderful weekend. Poke me in the Discord or send me an email if you have any questions, and I'll see you next week. Take care.